Welcome to the Deep Dive Books channel, where we hope you find something valuable every day.
I wanted to title this video, The Mystery of the Origins of Everything, but it might not be much of a mystery. Physics has a fairly clear understanding of the origins of everything in the universe, leaving only one small unresolved puzzle. Today, we'll focus on that puzzle. Once you understand it, you'll likely feel more awe than confusion. Simply put, everything around us is made of atoms. This understanding alone is remarkable. It means that, despite the endless diversity of forms we see in the world, their fundamental building blocks share similar structures. Protons, neutrons, and electrons. Neutrons help stabilize the atomic nucleus by working with protons. Protons determine the type of atom or its elemental identity. The number of electrons outside the nucleus determines the atom's chemical properties. As science writer Bill Bryson once put it, protons give an atom its identity, electrons its personality. Scientists have catalogued all elements in the periodic table, assigning each an atomic number based on the number of protons in its nucleus. The 92nd element is uranium, used in nuclear power plants and weapons. It's the last element naturally found on Earth. Beyond uranium, elements are called transuranic. These elements have such heavy and unstable nuclei that they can only be synthesized artificially in reactors and decay almost immediately. Elements beyond 118 are theorized to exist but have not yet been successfully synthesized. Here's an extraordinary fact. All 92 naturally occurring elements on the periodic table have been discovered on Earth. This means there's no magical element on a faraway planet that we cannot access. The universe doesn't hold us hostage. Imagine if there were a critical element Earth lacked, but aliens could use to make weapons. How troubling would that be? So, we are both lucky and humbled. Earth has everything we need. But this raises the question. Where did all these elements come from? Elements don't grow out of the ground. If you bury 10 gold bars in your backyard, they won't sprout an extra one over time. All elements originate from far corners of the universe. The first two elements on the periodic table, hydrogen, 1 proton, and helium, 2 protons, are remnants of the Big Bang. At the moment of the Big Bang, an extremely dense quantum field produced tiny particles like quarks and gluons. A microsecond later, as the universe expanded to solar system size and cooled, quarks grouped in threes to form protons and neutrons. These were the first hydrogen nuclei. About 3 minutes later, as the universe cooled further, some protons and neutrons combined to form deuterium, a heavier isotope of hydrogen with 1 neutron. Deuterium nuclei fused to form helium, 2 protons, 2 neutrons, and, occasionally, small amounts of lithium, 3 protons. The Big Bang could only produce these 3 elements. All heavier elements, those beyond lithium, come from stars. Without stars, the universe would just be a cloud of hydrogen and helium. Under gravity, these clouds of hydrogen and helium coalesce into nebulae, which then form stars. Uneven densities play a critical role. If the universe were perfectly uniform, stars wouldn't form. You can think of a star as a hydrogen-burning machine. Under immense heat and pressure, hydrogen nuclei fuse in the star's core, releasing energy that makes the star shine. Young stars like the Sun primarily fuse hydrogen into helium. Heavier elements form in the late stages of a star's life. When all the hydrogen in a star's core is burned into helium, the star begins to expand dramatically. Its outer layers ignite the remaining hydrogen, causing the star's size to grow exponentially until it becomes a red giant. At a certain point, the helium in the core accumulates to such an extent, under immense pressure, that helium nuclei undergo nuclear reactions. This process might trigger a rapid helium flash or occur more gradually, but the outcome remains the same. The core's helium is fused into carbon and oxygen. After the helium flash, the red giant's outer hydrogen forms a planetary nebula, a beautiful, luminous shell that will eventually be scattered by interstellar winds. Planetary nebulae are stunning. At their center is the leftover core of the star. For stars like our Sun, their relatively low mass prevents the remaining core, made of carbon and oxygen, from continuing nuclear fusion. This core will slowly cool over time, with its atoms crystallizing into a massive diamond-like structure. This is what we call a white dwarf, destined to spend the rest of the universe's life quietly and alone. To create elements heavier than carbon and oxygen and spread them across the cosmos, a star must have a mass at least 8 times greater than the Sun's. Such massive stars evolve beyond the red giant phase into red supergiants. In these stars, the core's carbon and oxygen undergo further nuclear fusion, forming elements like neon, magnesium, and silicon, and ultimately, iron, with 26 protons. This is a red supergiant on the brink of explosion. When iron accumulates in the red supergiant's core to a critical point, the immense pressure causes the core to collapse, leading to a massive explosion. A supernova. A supernova is one of the most brilliant events in the universe, capable of illuminating an entire galaxy. To distant observers, it may appear as a sudden, new star, as the actual star might have been too faint to detect prior to its explosion. But in reality, this new star marks the death of a massive star. The extreme temperatures and pressures generated by a supernova allow iron to react with free neutrons, electrons, and protons, forming heavier elements such as nickel and copper. These heavier elements are then flung across the cosmos by the supernova explosion. The scattered dust eventually coalesces into new planets, giving rise to Earth as we know it. We owe a great debt to supernovae. Truly, the death of one star gives life to countless others. Scientists once thought this was the end of the story. You may have heard of the term, GOAT, in sports, meaning the greatest of all time. For example, Messi is often regarded as the GOAT. In astronomy, there's a similar term called BOAT, which stands for the brightest of all time. On October 9, 2022, astronomers observed a boat-level gamma-ray burst, caused by a supernova explosion. This was a rare opportunity because modern technology allowed scientists to analyze the elements produced during the supernova explosion. The results revealed that almost no heavy elements were formed in this event. It had long been assumed that heavy elements like gold, with 79 protons, were created during supernova explosions. However, supernova events are rare, and previous assumptions were based primarily on theoretical models rather than direct data. This observation showed that supernovae are not responsible for producing heavy elements. So, where do these elements come from? Physicists had previously identified another mechanism, but it was thought to be exceedingly rare. As mentioned earlier, if a star's mass is less than 8 times that of the Sun, it will go through the red giant phase and eventually become a white dwarf. If its mass exceeds 8 solar masses, it will evolve into a red supergiant and then undergo a supernova explosion. After the explosion, the remaining core has 2 possible outcomes. If the core's mass exceeds 3.2 times that of the Sun, it will collapse into a black hole. If the core's mass is less than 3.2 solar masses, it will become a neutron star, primarily composed of neutrons. Thus, the ultimate fate of any star is one of 3. A white dwarf, a neutron star, or a black hole. White dwarfs, neutron stars, and black holes are essentially the remnants of dead stars. They exist quietly in the universe, remaining largely unchanged for eons. While black holes are beyond this discussion, let's focus on neutron stars. Normally, the story of a neutron star ends here. But under the right circumstances, if a neutron star encounters another neutron star nearby, they can be drawn together by gravity, spiraling into a collision that triggers a massive explosion. On August 17, 2017, scientists were fortunate to detect a neutron star merger. It happened to coincide with the early testing of the newly launched gravitational wave detector, LIGO, which we had previously analyzed. What went unnoticed at the time was that this neutron star merger produced a large amount of heavy elements, including gold equivalent to 20 times the mass of the Moon. At the event's press conference, LIGO's executive director, David Wrightsey, even brought a gold pocket watch inherited from his great-grandfather, saying, "This gold may have been created in a neutron star merger billions of years ago." This makes sense. If supernovae are not responsible, then it's reasonable to assume that all elements beyond zirconium, with 40 protons, on the periodic table were formed during neutron star mergers. This isn't just about gold. Without neutron star mergers, Earth wouldn't have elements like tin, iodine, tungsten, mercury, or lead. Many of which are essential to life and technology. However, there's a problem. Neutron star mergers are extremely rare. Since 2017, over 100 gravitational wave events have been observed, mostly black hole mergers, or black hole neutron star collisions. Neutron star mergers, apart from the 2017 event, have only been observed once more, and that instance wasn't intense enough to produce any heavy elements. Ethan Siegel, a theoretical astrophysicist and science writer, argues that neutron star mergers alone cannot account for the abundance of heavy elements. He has proposed several possibilities. Perhaps the early universe experienced more frequent, high-intensity neutron star mergers. Perhaps larger supernovae could produce heavy elements. Or perhaps some red supergiants can generate heavy elements internally. However, none of these hypotheses currently align with observational evidence. Thus, the origins of Earth's vast abundance of heavy elements remain a mystery. Heavy elements are not evenly distributed throughout the universe, but they are found in many places, and Earth is not unique in this regard. Still, neutron star mergers are extraordinarily rare events. Just consider how unlikely it is for one neutron star to encounter another. Only about 10% of stars in the universe are more massive than the Sun, and an even smaller fraction collapse into neutron stars. For scientists, such mismatched, observational data represents an exciting opportunity. They certainly won't throw up their hands and declare, "Physics is over," before despairing. Instead, these discrepancies offer the potential for groundbreaking discoveries. Every inconsistency is a chance to uncover something new. For the rest of us, it's fascinating to ponder that, the gold in our homes might have such a cosmic and mysterious origin. Thank you for watching, and I'll see you in the next video.
If you feel there is value in this, please like, subscribe to this channel, and leave your thoughts or suggestions in the comments section. Let's grow together and read more good books.